All right, welcome. In this video, I'm going to be showing you how to use a graphing calculator to analyze polynomial functions. And I'm going to be, in this video, I'm going to be using a TI-84 Plus Color Edition, just the kind of the most common one right now. But what I'm going to show you can be done with other graphing calculators. So let's just get to it. Let's see, what did I tell you all about? This was a couple of days ago for me. All right, using technology to analyze polynomials. Okay, we'll need to graph a function on an appropriate viewing window. I do think that a lot of y'all have experience with that. And in fact, let's start with that. Let's graph p of x equals x to the 3 plus 9x squared plus 12x minus 4. Okay, that is some other polynomial. Okay, so x to the 3 plus 9x to the 2 plus 12x minus 4. Okay, now we're going to be, zooming to the standard window typically in this class, and it depends on what the last thing you graphed was on your calculator. If you can't tell, we're going to zoom. We're going to press, instead of just pressing graph and going to whatever window it wants, we're going to press zoom, and then we see zoom standard is 6, so we're going to scroll down to 6, choose it, and then that'll set us from -10 to 10 in x and y. Okay, but then I can see it's like, okay, I can see the 3 zeros as a third degree polynomial. I know there's going to be 3 of them. I can see all 3 of them, but I can't see that I was reaching at the computer screen. Can't see that top of the graph, right? That local maximum. Now, I did this example a couple of times in class, and we found that if you go to, if you expand the window to y equals 50 in the upper range, you'll get the whole thing. So I might do that. And then there we go. Now we can see the whole graph, and that's going to be a much better picture for us. Okay, that's going to be the sketch. I think I envisioned when you were going to make the sketch that you would be annotating it and stuff, especially if you didn't have your own calculator. Finding the zeros of p, well, there's 3 of them, so I'm just going to set up 3 x coordinates. Those are the zeros, the x coordinates that make y equal to 0. And then we're going to calculate these zeros. Now, all the good stuff, in my opinion, I'm not a statistician, all the good stuff in the calculator, or the TI-84, is right there on calculate. So to get to the calculate menu, we have to press second, because calculate's in blue, and press calculate. And then I go over here, and I'm looking to find the zeros. So I say calculate a 0, number 2. Okay, now it's going to say left bound and right bound. Okay, what that means is it needs you to narrow down the area to search. So I can see that this first 0 that I'm kind of nearby, it's happening between x equals 0 and x equals 1. So I'm going to say it's between 0 and 1. 0 is my left bound. So I'm going to type in x equals 0 and press enter. Now it's going to ask me for a right bound, and that's going to be x equals 1. And see how you've got these little arrows here. It's saying, hey, I'm going to search between these 2 arrows for a 0. And okay, if there's only one 0 in your interval, you don't even really need to give it a guess. That's where we get 0.275. And in this class, we will always round to 3 decimals when we get our answer from a calculator. Okay, now I'm going to calculate another 0. This time, I'm going to show you how you can just scroll, right? We can just tap to the left until I go to the left of the 0, and we can pin it in that way. It doesn't matter. You can type in the bounds. You can scroll to get the bounds. It does not matter. Okay, the 0 I got was x equals -2. This thing here, 2 times 10 to the -12. Okay, that's not good mathematical notation. Don't ever, give me e as a times 10 to that thing. We don't want that. If you're going to use scientific notation, use scientific notation. This is not. But 2 times 10 to the -12, that would be 2, but with 10 zeros before it and after the decimal place. That's a really small number, right? And might be 11 zeros. I forget. We don't work much with scientific notation in my class. But that means 0. That's round off error in the calculator. Something times 10 to the -12, that's so small, it means 0. Then I'm going to calculate one more 0. I'm going to say that the left bound is looking like -8, and the right bound would be -6. Kind of counting the tick marks. And give it a guess, and I get 9.275. And I think that these have the same decimal. I think that's a coincidence. I'm not certain about that, but you would need more tools to be able to figure that out. Okay, find the x value at which p has a local minimum. And I'm having some glare, so I'm thinking maybe I'll just finish this example problem and I'll cut the lights off above me. Okay, so local maximum, okay, I may have read that wrong. Local maximum is happening right there. So I'm going to calculate again. a maximum. Okay? And this works pretty much the same way. We have to give it a left bound and a right bound and a guess. So we give it a kind of a narrower window to look in. Okay, that was the maximum where the function went from increasing to decreasing. And the guess, okay, again, there's only one maximum, it doesn't really matter. That maximum is occurring at x equals negative 5.236. Okay, find the intervals on which p is decreasing. Okay, well, it's going to be decreasing from after that maximum and until the later minimum. So I know it's going to start at negative 5. And I just need to know the kind of the right edge of when this thing is decreasing. It decreases all the way to here, and then it'll resume increasing. So we'd calculate a minimum that's between, I'd say it's between negative 2 and 0. And I'll get that at negative 0.764. Okay. And then find the exact values of the zeros of p. Okay, I don't have a whole lot of time when I'm recording this video, unfortunately. I would love to do this by hand. I'm going to really quickly scratch in my work, and you can just see how it would work. All right, there you go. So, noticing that we found that one of the zeros was an integer, we could run that through synthetic division, be left with a quadratic, and then that's something I could use the quadratic formula on. And so I got negative 2, the one we already knew about, and those other two are going to be negative 7 plus or minus the square root of 57, all divided by 2. And that's how we would do that if we needed to find the exact value. But the focus of today's lesson was using the calculator, so let's use the calculator, right? Okay, so the next one is consider the polynomial function f that is a 5th degree polynomial. Okay, so we need to go back to y equals, and we need to type this in. And I also need to get this glare situation. All right, so I typed in the polynomial here, x to the 5 minus 3x to the 4 minus 4x to the 3 plus 12x to the 2 minus 5x plus 15. All right, that was a lot of typing. And we're going to zoom back to the standard window, right, because we had adjusted the window earlier, so we're pressing zoom and 6. Okay, and then, okay, there's a lot of activity here. It's a 5th degree polynomial. I can't see what's all going on here. But I know that I forgot what I need to adjust the window to. I think I'm going to take a risk and only bump up y to like 30. Let's see how that looks for us. Okay, that was close, but not quite it. Maybe I'll switch that to 40. And then regraph one more time. Okay, yeah, that's perfect. I think, yeah, we can see that maximum up there. So that's the sketch of the graph. If you want to sketch one in for yourself, so you can, if you go back and look at these later, that might be a good idea. For what positive values of x is f of x less than 0? Okay, f of x, that's the y coordinate. Y is less than 0 down here, and also in this little bit that dips below the x-axis. These are not positive x values. So positive x values that make f less than 0 is just going to be between these two zeros. So I need to calculate those two zeros. And I'm going to scroll because these are pretty close together. Okay, found one. Okay, so x equals 2.236. And then the other 0 is going to be over here at x equals 3. Okay. I guess that would make sense that 3 could be a 0. 3 divides 15, rational root theorem, right? So that's the values of x that are positive that make f less than 0. Find the x-coordinates of all relative extrema on the graph. Okay, I'm seeing a minimum right here. And seeing, okay, x-coordinates, so a minimum at x equals 2.679. A maximum, that looks like a maximum to me over here. Yeah, it went down, up, down. Okay, so there's a maximum at x equals 1. Okay, 1.0000, like a bunch of zeros and a 9, that's just round off error. That's x equals 1. Okay, but then there's going to be a minimum right down there to the left of that, pretty close to 0. So I'm going to calculate a minimum. 0.245. And there's going to be one more maximum over here. Yeah, there should be 2 of each, yeah. So a maximum, I'm just going to go to the left of this thing. Okay, it looks like it was slightly off screen. The maximum having it y equals 40.245, but the x-coordinate was negative 1.524. If you want to learn how to solve for the exact values of these things without using a calculator, you should take my calculus class. I'm just going to plug that right now. Okay, intervals on which f is increasing. Okay, so when x is less than that first minimum, we've got increase, right? We're moving up as we move left to right. So if x is less than negative 1.524, we're increasing. Now we're going to be increasing very briefly in that middle section, but I might say over here that last minimum, which was at 2.679, if we're beyond that, it's also increasing. Okay, but then also between the x equals 0.245 and x equals 1, we're going to be increasing as well. Okay, f is decreasing everywhere else. Okay, that's a little frustrating. So it's going to be from the local maximum, negative 1.524, right here, down to that local minimum, which happened at 0.245. Okay, it looks like I'm writing these as intervals. And decrease, and then another interval of decrease would be right there from x equals 1 to this minimum, which happened at 2.679. Okay, so by these, I mean the intervals of x between these two values. Okay, those are the intervals of decrease. The complex roots of f. Okay, I am just going to I would love to do this problem. What we're going to do is we're going to find, what's the other root? How am I supposed to find the complex roots of f? I guess with the rational root theorem? Oh, you can see on the graph that x equals, that's going to be 1, 2, 3. It's a 0. Okay, we would run that through synthetic division, and I think then we would reduce it a little bit more, and we would eventually be able to find the two complex roots. I'm not going to have time to do that in this video, and I sincerely apologize. Okay, and now there is one more example I need to do for you, talking about an absolute maximum. Okay, but before I go, I forgot, go on to the next one, I forgot there was another thing I want to be able to do with this function, and I want you to be able to find the values of x that make f of x greater than 45. So I'm going to need to adjust the window on this, right? Because I only set my window up to 40. So let's just make this a 50. And then let it graph again. Gotta be patient. Okay, yeah, great. So 45, y equals 45 at about there. Beyond that point, to the right of that, y will always be greater than 45 because we know about the end behavior of a fifth degree polynomial with a positive leading coefficient. Pardon me. So what I'm going to do is I'm going to figure out where the polynomial equals 45 by graphing 45. And see, there it is. And where they're equal is right where those lines intersect. So I'm going to use the calculator to calculate the point of intersection. So we're going to go over here, and we're going to calculate. Again, that's where all the good stuff is. Intersection is number 5. First curve. Okay, we can see it really nicely on this one because this is one of the color edition ones. The first curve is the blue one. It's y1. If for some reason you were graphing 3 curves and you were trying to intersect only 2 of them, you're only ever intersecting 2 of them, but you were trying to intersect 2 of them and you weren't on the right one, you can press the up and down to switch between the 2 curves. See how I pressed down and it went to y2 equals 45. I press up, it goes back to the blue curve. We only graph these 2, so I'm just going to press enter for the first curve, enter for the second curve, give it a guess. Who cares? There's only one intersection. This is x equals 3.482. Okay, so I'm going to say f equals 45 at x equals 3482. Okay, I'm going to say f of x is greater than 45 to the right of that intersection, so that's when x is greater than this number. Okay, so it's like the other inequality we solved, except we had to use intersect instead of calculate 0 for that one. Okay, now there's one more example I've got, and I need to just make sure it's going to work. All right, the last example I've got for you is find the absolute maximum value of f of x. And that's something that I saw in the homework, but I didn't see in the pre-printed notes, so I figured I'd throw on a case of this. Okay, so f of x equals negative of x plus 3 squared times an x minus 2. Okay, so we're going to graph this, and I'm going to show you what I mean. So we're going to zoom to the standard window. And okay, so I've got a fourth degree polynomial with a negative leading coefficient, so I know that the arms are going to open down. There is some maximum up here that is the very highest point on the graph of f. Okay, you can also ask about an absolute minimum if you have a point that is the very lowest point on the graph. There is no absolute minimum on this one because as negative of a number as you want, we can find an x value that gets us there, right? Because we know that on both sides it's going down. So we need to just adjust our window. I think I'm going to just change y from negative 20 to 20, maybe. Oh, whoops, pardon me. That's clearly not right. Hey, if you ever go start to graph and it doesnn't look right, and because I stopped it right there, what I did was I pushed the buttons that would turn the calculator off. That stops it from graphing. And sometimes, especially if you type in something wrong and it's taking a really long time to graph, you don't want to sit there and wait for it to graph. You just want to fix your error. Okay, so that was what I did right there. Okay, I'm changing it from negative 20 to positive 20 so I can see the whole graph. I'm hoping, yeah, there we go. All right, and then I'm looking for this maximum. That's the absolute maximum. When they say the maximum, it's the biggest maximum of all. A maximum is just any old place where the function goes from increasing to decreasing. Okay, so this over here, we're going to calculate a maximum. I'll give it a left bound, give it a right bound, give it a guess. And I'll get, okay, x equals 1.225 and y equals 16.947. But the thing is, it's asking you for an absolute maximum value of f. And remember, y is equal to f of x. So they're really asking for the greatest y coordinate. There will be a time, in a later class, probably in calculus, when they ask you for the x, or the independent variable value that gives you the absolute maximum, because you might be interested in, say, finding the time at which there is the greatest number of people in the cafeteria at lunch or something, right? If you were concerned with like fire safety or something. But for us, we're interested in the actual maximum value of f, which is going to be the y coordinate here. So I'm going to say, the maximum value of f for any real number input. Okay, that's all I got to show you for today. You need to practice all these skills using the graphing calculator because that's something we need you to be able to do for this class and later classes. But these are all the skills we need you to have for Algebra 2. So that's it. Thanks for watching.